move in a straight line through curved space-time, and this stage is stopping me. The Earth is stopping me, and it's that force that I feel as the force of gravity holding me to the ground. Now, gravity probe B was tested at, this is Einstein's theory, by the way, that's Einstein's equations of general relativity. The R bit is the curvature of space and time, and the T bit is the distribution of energy and matter in that space and time, so the Earth, essentially. That's all you need. What gravity probe B did was it orbited around the Earth with two things called gyroscopes. So simply actually, they were the most spherical balls ever built in the history of humanity, which is, I've never said, I don't know, it's a nice sentence. What they do is they spin around, and they have a spin axis, so they're like a little spinning top. The satellite orbits around the Earth, and there were two effects that were measured. One is called the missing inch effect. So imagine I draw a circle on a piece of paper, and I want to curve that piece of paper into a cone. Then I have to cut a little triangle out of the paper. I just have to cut a little bit out and I fold it into a cone. Well, the Earth has that effect on space-time, and it was calculated way back in the 1920s that that effect in a full orbit of the Earth would be one missing inch of space-time, just the curvature. That means that when you send the little gyroscopes around in orbit, then they don't go around the full 360 degrees, and so the axis of the gyroscope, which moves a little bit, doesn't come back to quite where it started. Gravity probe B measured that, and it was in exact accord with Einstein's theory. The other thing it measured was even more subtle, it's much more difficult to explain, but it was an effect, again, a shift in the gyroscope spin axis, and it shifted by the amount that if you look at Pluto from the Earth and measure the angle between the north pole of Pluto and the south pole, then that's the effect that it measured. And again, it was calculated in Einstein's theory, and it was measured, and it was in precise accord with Einstein's theory. Now, you might say there's a very small, insignificant effects, but there are places in the universe where it's thought that they may play a very profound role. This is a galaxy called M87, which is a giant galaxy. It's 10 times the size of the Milky Way. There are over 1 trillion stars in this galaxy. The Hubble Space Telescope took a picture of the centre of the galaxy, and this is it. And you see that there's a strange structure emanating from the centre of the galaxy. It's actually a jet of high-energy particles and radiation streaming out from a black hole that is over 2 billion times the mass of the Sun. So there's a giant black hole, which, if you put it where the Sun is in our solar system, would extend beyond the edge of the solar system, one of the most massive black holes known. And somehow that black hole coronates this jet. That jet you see there is 5,000 light years long. In fact, its influence extends out 250,000 light years. And one of the ways, one of the theoretical propositions for how it does that, how it controls that beam that we see in the pictures, is the effect that the curvature of space and time around a black hole, or the effect that from the Earth is that tiny bit of measurement, the angular size of Pluto in the sky. So those effects, although they don't have a big effect around Earth, have enormous consequences out there in the universe for the most massive objects in the universe.